Okay, so we're going to finish our last little bit of chapter 10, which is net ionic equations. This used to be an enormous part. There used to be an entire question, open response question, on the AP exam about net ionic equations every year. They've taken that away, but we still need to know how to do it. Oh, sorry, we we forgot our complex example of redox before we get to net ionic equations. My goal is to finish it right now. All right, so what is oxidized and what is reduced in the following reaction? Sorry, so we remember the other day on Wednesday we were doing redox reactions. So we need to figure out what the oxidation number is for each one to figure out if it's oxidized or reduced. So I'm just going to go through and do it quickly because we don't have much time. H plus is 1. It's the charge. O is going to be minus 2. So I have 6 times minus 2 is minus 12. So I have S, 4S plus a negative 12 equals negative 2. So S actually comes out to be 2.5, which is weird, but you won't see that very frequently, that it comes out to be a not whole number, but it can happen. Al, elemental Al is what for oxidation number? 0. All right, so H plus 1, S is minus 2, Al plus 3, H plus 1, O is minus 2. So what changed oxidation states from the reactants to the products, Eugene? Sulfur. So sulfur went from 2.5 to negative 2. So does that mean it gained or lost? Gained electrons. So it was reduced. So what else changed? So, yeah, okay. Aluminum went from 0 to plus 3. So it lost electrons. So it was oxidized. For now, that's what you need to be able to do, is look at a reaction, figure out what was oxidized and what was reduced. Okay, so moving on to net ionic equations. This actually is a net ionic equation, but we wouldn't call it such. Yeah. Yeah, Eric. So the question was, does this oxidation happen in every single reaction? The answer is no. Oxidation reduction doesn't happen in every chemical reaction. So if you have like the partner swap reaction, there's no oxidation reduction. You just have these ions that are changing oxidation state, right? Acid-base reactions tend to, for now, not have oxidation reduction. I'm trying to think if there are other cases where it might. There might be cases, but in general. So this is really when charges are changing. Synthesis, decomposition. So this is, yes, redox is its own category, but synthesis and decomposition oftentimes have elements of this, right? Because you're changing oxidation state by moving electrons in between different things. So like if I react sodium metal with chlorine gas to make sodium chloride, I'm actually transferring electrons, right? We've talked about that in ionic bonding. So that's an example of a redox reaction. Something's gaining or losing, but it's also a synthesis. So this can be, things can be more than redox. They can fit into other components. All right, so net ionic equations. So for reactions in aqueous solution, like most of the partner swapping reactions, and redox, we can often write the chemical equation in simpler form. So we have this example reaction right here. If I write this out as what it actually looks like, I'm going to run out of space. So I'm going to write it. Yeah, I know. Thank you, guys. Thanks. I'm trying to get better at it. It would look like this because bless you. That was a very good sneeze. All right. Sorry, I missed a couple AQs. But look at, I can write this more simply. NO3, as it states right below, that I actually caught this time, it's unchanged in the reaction. So why do we need to include it at all? NO3 starts out as an ion in solution, and it ends up as an ion in solution. Nothing changed with nitrate. So if nothing changed, why do we care? The answer is we don't. Spoiler alert. I'm getting loopy. End of the day on Friday too. All right. Does anybody need me to wait? Yeah, I heard yeah. Well, we're waiting. Does anybody still go trick-or-treating? No? Shall? All right. Maybe. I remember I was so mad when I was a senior in high school and my parents wouldn't let me go trick-or-treating anymore. I'm like, it's free candy! Free candy's the best! And they're like, dude, you have your driver's license. You can't go trick-or-treating anymore. If you can drive yourself, it's not okay. All right. Yeah. Okay. So, net ionic equation. Oh, did you get your license, Ellen? Congrats. All right. So, yeah. Net ionic equation is a chemical equation that shows only the species that change in a reaction. So that's taking out things like nitrate in that last reaction that didn't change at all, which are called spectator ions. See, these are ions that don't change state. Same on both sides of the equation. All right. Does anybody need me to wait for another second? Okay. So I already sort of did this. Ooh, that was fancy. You want to see that again? All right. Wow. All right. So to write the complete ionic equation, start with the balanced equation, like we did. So I already sort of wrote this out for you. Whoops. This becomes all right. So anything that's aqueous that is ionic or is a strong acid or base. Strong acid. Write it as separate ions. So you take like AgNO3 is ionic in solution, split it into its ions. Like HCl, strong acid, you would write it not as HClAQ, but H plus AQ plus Cl minus AQ. The question came up earlier, like, do you have to write the AQ? You should for the ions. You could also technically have an ionized gas. Did you? So apparently in honors chemistry, people got a lot of points off quizzes for not having the states of matter in. We're just get in the habit of putting the AQ for the ions. Okay, so now what does this become? We can remove the nitrates from both sides. Gone, and we're left with this. So now this is your net ionic equation. So the nitrate didn't change at all. The nitrate didn't take part in the reaction. Therefore, it's not there. There's another thing in chemistry that is the same at the beginning and the end that we actually leave out of all of our chemical equations. They make reactions go faster, or what the catalysts, right? So it's almost, we leave catalysts out as well because they don't change. Just like here, nitrate didn't change. It's not a catalyst in this case. It just didn't change. Okay, so here are your tips. Precipitation reactions. So figure out solubility and only substances that make the solid are involved. So if you have a precipitation reaction, your net ionic equation, you start with your product, which is the solid, and then your reactants are just the ions that make up that solid. All the other ions are spectators. Acid-base reactions with strong acids split into ions. This often just becomes this. So your strong acid, if you have a strong acid mixed with a strong base, this is generally going to be your net ionic equation. And this is almost always on the AP exam. And redox reactions, find Leo and Gur. And go from there. All right, so the next 3 slides are examples. So I'll do one together, and then I'll probably just I'll do the rest as like after you guys leave, or like as you're walking out the door. So, okay, so solution, solid, solution. Let's take our little hint. So to do precipitation reactions, we start with our solid. Yeah, Eric. The example we did previously was not any sort that we had done. It wasn't a precipitation reaction. So it's actually what we call a single replacement reaction. But that's not one that they want us to understand necessarily. So just under it, you can think of that one as just a redox. So here, what are the things that make up this? Well, I have my SO4 2- over here. Oops. Plus my 2Ag plus. And that's my net ionic equation. So you would know to split. If you wanted to do it all out the long way, you split up all your ions and cross them out. Same thing is true for here. Start with my solid. This is why you have to know that this is a precipitation reaction. If you didn't know, then you couldn't just make the steps like that. Here it's 6 Br minus plus 3 Pb 2 plus AQ. Why is it 6 Br minus? Because for every mole of AlBr3 that splits apart, you get 3 Brs, and your coefficient is 2. So as it splits apart, it's not like you're going to have 2 Br3s. They totally dissociate in water, so you're left with 6 Br. So yes, this is Eli's freestyle rap. Note, if you're captioning this, it's your choice whether or not you want to do it or not.
All right. Don't even need to mention the chemistry. We sitting here on the 4th floor. Never know what's going to be next in store. Headed to the door because I'm about to be leaving. Mr. Bennett, have a nice evening.
The musical musings of Eli. Now I will continue lecturing to an empty room so I can finish this. All right. So writing net ionic equations examples. Here we're noticing that this is an acid and this is a base, strong acid. So we're going to assume it completely dissociates. And we're going to start with our 2 water molecules. And so we know we get 2 H pluses from our acid plus 2 OHs from our base. Oh, there's a pretend question. The pretend question is, Mr. Bennett, can I just simplify this into H plus OH minus makes H2O liquid? Well, yes, you can. That's a wonderful question. Thank you very much. I was waiting for that one. Now here, on the other hand, this is, whereas H2SO4 is strong, acetic acid is weak. So we actually have to leave this written out like this. So I'm actually going to write this whole one out. Because this is a solution. All right. So now we have to look to see what's the same on both sides. We cross out the Ca2 plus, and we are left with this as our net ionic equation. And note that it's different from the one, oops, erase. It's different from the one above because here I actually have to keep my weak acid together. Remember, it doesn't dissociate completely. And you can keep the coefficients as 2, or you can take them out. All right. Woo. Another acid-base reaction. Phosphoric acid, we say to ourselves, okay, is this a strong or weak acid? Well, it's weak, so I'm going to have to do the 2H3PO4 AQ. It doesn't dissociate, it stays as a molecule. Here's a solution, so I have 3Ba2 plus AQ plus 6 OH minus AQ. Makes a solid, which is Ba3PO4 2 plus 6 H2O liquid. Well, in this case, everything changed, right? So my net ionic equation would be merely splitting up the barium hydroxide. All right, the last one we have. This is a redox reaction. Let's just write it all out. All right, solution. So I do 3Cu2 plus AQ plus 6Cl minus AQ. Makes, okay, solution again. So I split it up. 2Al3 plus 6Cl minus plus 3Cus. All right, well, what changed? Well, my 6Cl minuses are the same on both sides. So 2 aluminum plus 3 copper ions make 2 aluminum ions. Oops, forgot the AQ up there. Forgive me. And I'm getting feedback from Mr. Hamill that I'm not nearly enthusiastic enough. This is fun. I love it. Let's do redox. Let's enjoy it. What's Leod? What's GERD? All right. Well, Al goes from 0 to plus 3. Copper goes from plus 2 to 0. So aluminum loses electrons. And copper gains electrons. All right. So I apologize with this at the speed with which I flew through net ionic equations. There's plenty of practice on the problem set. Now, go through. This is what you should be able to do. Recognizing reaction types. You should be able to balance chemical equations. Identify the strong acids. Write net ionic equations. Identify oxidation state, and identifying the oxidation and reducing agents in an oxidation reduction reaction. So the oxidation and reducing agents. These are the vocabulary is a little confusing. The way I think about it, if you're a grammar person, is passive versus active. So if something is oxidized, that means it reduces the other thing. If it is reduced, that means it's oxidizing the other thing. So they're called oxidizing agents and reducing agents. All right, thank you for listening.